Hi everyone. Welcome to the presentation on the paper FRAUDAR, Bounding Graph Fraud in the Face of Camouflage, offered by the Stanford Scholar Initiative. This paper talks about detecting fraudulent activities performed on the internet using graph-based methods. So, let's go over the problems faced in detecting fraud cases. Being a part of a highly networked society and depending on its connections makes us more exposed to these fraudsters who pretend to influence the image and credibility of companies or people. Today, fake followers can cause an irreparable damage to a brand. Let us understand the challenges we face in solving this problem. The general difficulty of fraud detection is due to the factors as presented in the diagram. Digital fraud detection has become a race between fraudsters and analysts who are detecting them. In the image, we can see the graph-based approaches involving subgraph mining, clustering, and the camouflage-resistant FRAUDAR algorithm. Every follower-followee or product review graph has some density of interlinking. Camouflage is when fake links are added to increase this density and make an account seem authentic. Camouflage is used to simulate real activity for fake accounts. Attack refers to an approach to detect fraudsters and counterattack the attempt to avoid it. There are three types of camouflage. The effect of camouflage on the graphs can be seen for each case. In all graphs, a single dot represents an edge between an object and a user. Camouflaging adds extra edges and increases the graph density as shown. In order to detect fraud, the algorithms need to detect abnormal density, be resistant to camouflage, and finally provide an upper bound on time complexity. Let's take a look on what sort of questions need an answer. Questions we seek to address revolve around some key ideas with regard to fraud detection, the approach taken, and the time bound for scalability. We seek to answer the what and the how with regards to detection and quantification of digital fraud as well as efficiency of the detection algorithm. So let's take a look at the exact algorithm used in developing FRAUDAR. People buying fake followers or reviews have many connections between them and the hired fraudster accounts. A review given by a user for a certain product establishes a connection or an edge between them. Say we have a bipartite graph with E edges and V vertices where one set is the users and the other set is the objects. FRAUDAR has a camouflage-resistant density metric to detect suspicious nodes and unexpectedly dense regions, such as a product with unusually high user reviews. Choosing an appropriate data structure, the algorithm runs with a near linear time complexity. The class of metrics defined for FRAUDAR allows for a theoretical upper bound to undetectable fraud and camouflage resistance.
We now examine how the authors carried out their experiments. The method proposes a density metric g of s defined as shown in the formula. The function g has a good mathematical form because it only depends on the union of users and objects chosen. The right behavior of the metric is based on the suspiciousness function, whose properties are exploited throughout the algorithm. The major advantage of this metric is that it is scalable, robust to camouflage, and has a theoretical guarantee of provable upper bound on undetectable fraud. These positive properties are achieved by taking great care while defining the metric. The FRAUDAR algorithm was tested on both synthetic and real data. For synthetic evaluation, 200 fraudulent entities were added to a graph of 2,000 entities. FRAUDAR performed the best, with close to ideal results on each of the four types of camouflage as seen on the right. Real-world Twitter account data was also used to evaluate the algorithm. The accounts detected by FRAUDAR had tweets offering follower buying services and they had not been deleted since the 7 years the data had been available. On a Twitter graph with 41.7 million users and 1.47 billion follows graph, FRAUDAR detected a dense subgraph of size 4031 followers by 4313 followees. It used samples from this set for experimental verification for its efficiency. FRAUDAR outperforms its competitors in a number of large datasets, including Amazon, TripAdvisor, Ipnion, and Wikivote. We now move on to the results of these experiments. The four main outcomes of the research are as shown: camouflage resistance, effectiveness, and theoretical upper bound. Let's review the questions based on our findings. The summary of how the answers to those questions were obtained are shown in the green bubbles right next to the connected gray boxes. Now let's summarize our analysis. FRAUDAR algorithm has three key facets as we can see in the image. With that, we come to the end of this presentation. We hope no fraudsters are watching, and if you are, hope you understand that camouflaging no longer works. If you would like to view more of these talks, visit scholar.stanford.edu. Thank you.